Well, this being the first lesson in Unit 2.2, we've moved on from just describing Newton's laws and into further applications of Newton's laws. And one of the areas of emphasis is a unit of study known as static equilibrium. Let's break that down a little bit. Static just means at rest. A lot of times we talk about static electricity, so that's due to the electrical properties you get when charged particles come to rest on the surface. So we often drop the word electricity and just talk about static, right? On a really windy day, you say there's a lot of static in my hair, in my clothes. What you really mean is there's static electricity. Here we're talking about static equilibrium, not static electricity. So static strictly means at rest. And equilibrium, as you know, is just a term we use when the sum of all forces acting on an object is equal to zero, which always means that the acceleration is zero. But that doesn't always mean an object is at rest. Acceleration equals zero could be one of two things. It could be at rest, or the second object could be an object that moves with constant velocity. But when we combine these, right, we're saying static, at rest, equilibrium, net force is zero. So static equilibrium is indeed just the study of systems that stay at rest, okay? So that means that whatever free body diagram it represents the situation, it's got to somehow illustrate the idea that all the forces combined to give zero net result. So one example might be hanging something like a piñata. If the piñata hangs from two strings of unequal length, then the amount of tension in string number 1 is certainly different than the amount of tension in string number 2. So those are, well, without a doubt, two forces that are acting, and gosh, we know what the third force is, right? Never get away from this one. There's this downward pull of gravity acting on the piñata. So how do all three of those forces, the weight of the piñata, the tension in one string, and the tension in the second string, demonstrate this concept of equilibrium? Make a free body diagram and see if we can figure out these values. So let me add some numerical values to the problem so we can turn it into something that can be solved all the way through to a final answer. What if this piñata has a mass of, how about 6 kilograms? And I won't give the values of the tension, but I will tell you that the angle here is 30 degrees, and the angle here is 50 degrees. So then, without a doubt, the angle here is, well, it's definitely not 90. So we can't just use right triangle geometry to figure this out. But we can make a resolved free body diagram if we first start with an unresolved diagram. So how about we draw the weight vector first? Okay, now the relative size of all our vectors is important. We can't just draw these in arbitrarily. I know one of the tensions points along this direction, a little steeper, and another tension vector points a little flatter along this direction. But I don't think that's a very good representation of the magnitudes of those forces. I'll show you one thing. If those were the correct magnitudes, notice what's going to happen when we break everything into its components, when we resolve the free body diagram. You can probably see it already. This doesn't represent equilibrium. If I drop a vertical line straight down through the tip of each of these tension vectors, you notice what I notice? The tension pulling to the right due to T1 and the tension that pulls to the left due to T2 are definitely out of balance. And if that were the case, the net force along the x-axis wouldn't be zero, and our piñata would not be in equilibrium. It would be accelerating to the left. So this encourages me to edit the length of my vectors a little better. Let's see. There's got to be a quicker way to do this, but here we go. Well, what if I just draw tension number 1 this length? Then I know tension number 2, since it pulls a little flatter, doesn't have to pull as hard in order to have a horizontal component that offsets the vertical component. Let's see if this looks reasonable. We've got our x-axis and our y-axis. And now we illustrate the components by drawing lines straight down to the axes. Yeah, that looks good. This looks like the horizontal component of tension number 1 pointing to the right pretty well balances the horizontal component of tension number 2 pointing to the left. Now let's look at the vertical components. Draw some lines going across to the y-axis. So it looks like the vertical tension, or the vertical component to tension number 1 itself, isn't quite long enough to offset the downward pull of gravity, but notice we also have a little more upward pull due to the component of tension number 2 that pulls up, and that seems like a pretty good illustration of equilibrium. I've messed things up a little bit. I shouldn't really be resolving the forces on the diagram. I should draw a second free body diagram that shows all of the forces resolved. So 1, 2, 3, no, 4 and 5, huh? Let's label all these. mg, this is tension number 1 along the x-axis. This is tension number 2 along the x-axis. Draw an arrow to there. That's tension number 1 along the y-axis. And then stacked on top of it is tension number 2 along the y-axis. Okay. Oh, well, since this is static equilibrium and the net force is 0, the only way that could be true is if tension 1 on the x-axis in magnitude is equivalent to tension number 2 along the x-axis. And simultaneously, when I add tension number 1 on the y-axis with tension number 2 on the y-axis, combined, those have to be just as great in magnitude as the weight of the piñata. Well, these are all components that are found based off of things like sine equals opposite over hypotenuse and cosine equals adjacent over hypotenuse and so on. You see, if we've labeled this angle right here as 30 degrees, then that tells us this angle also has to be 30 degrees, and likewise this angle has to be 50 degrees. So I have a right triangle down here in which I know an angle of 50 degrees, and I'm trying to find basically what's the horizontal or adjacent side to that angle and what's the vertical or opposite side. So, for example, T1 along the x-axis is just T1 multiplied by the cosine of 50 degrees. So I can rewrite this expression in a slightly more detailed way. T1 times cosine of theta 1 has to equal T2 times cosine of theta 2, where theta 1 is 50 degrees and theta 2 is 30 degrees. Likewise, T1 times the sine of theta 1 plus T2 times sine of theta 2 is equal to mg, and again, where theta 1 is 50 degrees, theta 2 is 30 degrees, m is 6 kilograms, and g is 9.8 newtons per kilogram. I'm not so eager to plug in the numbers just yet. We can get there. Really what we have is a system of 2 equations and 2 unknowns, right? I can plug in values for everything except T1 and T2. So one way to do it is solve for T1 in terms of T2. Why don't we do that? If I rewrite this expression, I can say T1 is equal to T2 times the cosine of theta 2 divided by cosine of theta 1, and that becomes a quantity I can substitute in place of T1 in the second equation. And so if I do that, we get T2 times cosine theta 2 over cosine theta 1 multiplied by sine theta 1 plus T2 times sine theta 2 is equal to mg. I guess I could recombine. Well, sneak peek at another problem I have for you here. Let me get this out of the way. Sine of theta 1 divided by cosine of theta 1 would be what? Same as tangent of theta 1. So we could write it like this. Factor out the T2, right? T2 times the quantity cosine theta 2 tangent theta 1 plus sine theta 2 equals mg. So T2 is equal to mg divided by cosine theta 2 tangent theta 1 plus sine theta 2. So notice that I'm not too impulsive when it comes to plugging in numbers. I always like to do that as a very last step. It seems to be the most trivial part of the whole exercise. Often, when you keep things algebraic, every now and then, a simplified equation comes up, so when you see a similar problem, you could often just jump to a new equation that you've derived by keeping everything algebraic. Didn't particularly happen in this case, but for the sake of consistency in your work and being well practiced in that form of problem solving, I strongly encourage, as I think all physics teachers do, to keep your work algebraic for as much of the solution as you can. And finally, we end up at a last step for plugging in numbers. It looked like we were ready to start plugging in numbers way back here, but really, hold off until the end. So T2 is equal to 6 kilograms times 9.8 meters per second squared divided by the cosine of 30 degrees multiplied by the tangent of 50 degrees added to the sine of 30 degrees. All right, well, grab a calculator and see what we get. Okay, so if my calculator is not broken yet, I believe the tension in string number 2 is equal to 38.4 newtons. So what's the tension in string number 1? When we go back to our work, here by multiplying the tension in string 2 by this ratio of cosine theta 2 over cosine theta 1. So if we take 38.4 newtons and multiply it by cosine 30 divided by cosine 50, that should get it done. And we get tension number 1 is equal to 51.7 newtons. Now, does that make sense that tension 1 would be greater than tension number 2? I think so. Sort of, what's your instinct on this one? If you take your finger and you reach and you pluck this string, and then you take your finger and you pluck this string, wouldn't you expect the one that's more vertical to feel tighter? Yeah? So this one's 51.7 newtons, and the one that's a little more flat was, what do we say, 38.4? Okay. Static equilibrium. What's another example? How about this one? Would this be possible? Could you take, how about we call this one M1 and a second block with a mass of M2. So you tie a string and you connect block number 2 that's sitting on the desk to this ring. All right, there's a ring right here. And there's a string that connects to block 2, and then a third string that anchors this all over to the wall. Could this really be a case of static equilibrium? In other words, could this be a study of a system that remains at rest? I mean, block number 1 is going to have a tendency to fall, and block 2 is going to have a tendency to slide this way. So the only way this could work is if there's some force of friction, right? There's got to be something that can pull back in this direction so that this block wants to stay at rest, and then by virtue of the tension that remains in this string, there's an upward force to offset the downward pull of gravity. So again, if we were to make a free body diagram, we could figure out exactly things like maybe how much friction would we need, or perhaps the amount of friction is given, and we could figure out what's the greatest or smallest, what's the critical value of this angle right here. There's a few different ways we could ask the problem. It just depends. Maybe the angle is given and the friction values are given, and we're asked what's the largest amount of mass that could hang here so the system remains in static equilibrium. Well, I can't give you numerical values for this problem yet because it relies on an understanding of friction, and we have not yet had a discussion on how to compute frictional forces. That's one of the major points of emphasis for this unit of study on applying Newton's laws. So thanks for watching this lesson, and tune in for more as we move on to a study of friction.